So, welcome everybody in the world to our next plenary talk of the SIAM Conference on Imaging side. I'm very happy and it's a great pleasure for me to introduce Thomas Pock from the University of Technology in Graz. A short CV of Thomas. Thomas has received his master in PhD 12 years ago from the computer science engineering. It's called Telematik in Austria, from the Technical University in Graz. Then he went as a postdoc to the University of Bonn, I think at this time in the group of Daniel Kramers. But you may know that Thomas liked mountains and in particular sports in the mountains. And he had some calls from other universities. I know in particular he had calls from universities in Germany, but he decided to go back to the mountains, namely to Graz again, where he became an assistant professor at the Institute of Computer Graphics and Vision. And Thomas did a big job there. You may know the famous Chambol-Pock algorithms, famous in our society, I have to say. And he got some prizes and some grants. And so he got, in 2013, he received the start prize of the Austrian Science Fund. And in 2014, he got a starting grant from the European Research Council. And now he leads a very big group at the university in Graz, namely the group VLO, he called it. That means Vision, Learning and Optimization. And in 2019, he became also a reporter of the board of the Austrian Science Fund for the section of computer science. The focus of his research is in image processing, computer vision, and inverse problems, and as you know, in convex and non-smooth optimization, and of course, recently also in machine learning. And his topic is related to all of this, I think. It's on variational networks, and we are really looking forward to your talk. Tom, please go ahead.
Thank you very much, Gabriele, for this introduction. So thank you. And also thank you very much to the organizers to set up in such a short time this wonderful event, and thank you for the invitation to have this talk here. Yes, as Gabriele said, I will talk about something that is called variational networks, and I will explain a little bit to you the history of variational networks, so how we actually came to something that we now call variational networks. So everything in our models basically starts with a very famous theorem due to Bayes, quite an old theorem. And the big advantage of Bayes' theorem is that it treats both the measured data, so I will always call the measured data D, as well as the solution. We actually want to compute the unknown solution U as random variables. And this is actually important to tackle real-world inverse problems because, you know, the measurement data is subject to a stochastic process. We have noise in the measurements, and also therefore it's quite intuitive that also computing the unknown solution should be done in a framework that takes care of that. So that it means that we can assess the uncertainty of a certain solution U based on the uncertainties we have in the measured data D. And then everybody knows Bayes' theorem. It actually tells us that the posterior probability of the unknown solution U given the data, the measured data, is proportional to the likelihood of the data given the unknown solution times the prior. Okay, and when you have this formula, it's quite abstract, and it gives rise to several basic scientific questions, and some of them I would like to discuss on in my talk here. So first of all, the modeling. How should we model the a priori distribution P of U? How should we model the likelihood distribution P of D given U? Should we use convex models, non-convex models? Should we handcraft those distributions? Should we make use of learning? What about a forward operator in the likelihood? What about the noise assumption, and so on and so on? The second basic question is how should we actually, when we have decided we want to do some learning, how should we learn it? Should we use generative learning? Should we use discriminative learning? What about the loss function for learning? What about learning algorithms? And I put in capital letters data because nowadays with mainstream deep learning, basically the data plays the biggest role. So we should carefully select the data, and we should make sure that we have enough data to cover our space. The third basic question is inference. Once we have our models, once we have learned, how can we perform inference on our models? So the Bayesian approach delivers a complete distribution, the posterior P of U given D. Which kind of inference method should we make use of? Maximum posterior estimation that selects that example that maximizes the posterior distribution. Should we take the minimum mean squared estimate? This is that solution that minimizes the squared distance to all other solutions weighted by the posterior. Should we make use of mean field approximations, Markov chain Monte Carlo methods such like Langevin diffusion and so on? And all of you might know that those questions are still subject to intense ongoing research, and we are still far away from having good general answers. So only in very particular cases we have good answers to those questions. So let me briefly talk about modeling and inference. It's quite standard to make use of the following exponential distributions, which are well known from statistical physics due to Boltzmann and Gibbs. And these distributions are basically given as the exponentials of minus some energy of the configuration divided by the temperature. And the same kind of distribution we use both for the prior as well as for the data likelihood. The temperature T can also be seen as the variance of the configuration. In some inference methods, like in map inference, the temperature does not play any role, but if you, for example, do mean squared estimation, then the temperature actually plays a main role. In those distributions, the appearing energy terms, R of U is the so-called regularization term or smoothness term, sometimes also simply called prior, and in the data likelihood, the appearing energy D of U and D is called the data likelihood, data fidelity, or data fitting term. When we put those two terms together, according to Bayes' theorem, we see that it's actually an exponential of minus an energy divided by the temperature. And the energy is simply the sum of the regularization term and the data fidelity term. And this is simply the energy of the joint configuration of the unknown solution U and the measurements D. So when we have decided, and this is actually what we will do in the entire talk here, to make use of map inference, it means we would like to select that sample U from the distribution that maximizes the posterior distribution. Then it turns out that by taking the negative logarithm, it's equivalent to solving a minimization problem where we would find that solution U that minimizes the energy that is the sum of the regularization term and the data fidelity term. And the temperature clearly then is just a constant which you can simply neglect. So let me first talk about how should we model the likelihood term. I start with the likelihood term because in most applications this is more straightforward. A common assumption in all kinds of inverse problems in imaging is the following linear image formation process, where we say that our measured data D is some linear forward operator A times U or AU plus psi, where psi is some additive noise, for example, Gaussian noise or different noise, of course, can be considered. If we know that we have zero mean Gaussian noise, then the straightforward data fidelity term is simply the exponent of the Gaussian distribution, so we end up with 1/2 the squared norm of AU minus D. This can be applied to a variety of different problems in imaging, image denoising, deblurring, super resolution, magnetic resonance imaging, computed tomography, and so on and so on. Of course, if we have other types of noise, Laplace noise, Poisson noise, gamma noise, we should consider other data fidelity terms that might not be of this type. Could be, for example, L1 norm or the entropy or different other norms. In very recent work, we also consider learning the data fidelity term, where we make more general assumptions, such as assuming that we have a Fréchet metric or we have more general divergences. Here are a few examples how the forward operator looks like, or to which kind of measurement data it corresponds. In image denoising, where the forward operator is just the identity, it means that our measured data is simply the noisy image. In image deblurring, the forward operator is simply a blur kernel, so we write it here as a convolution of the clean image U with some blur kernel shown here. So the input data is a blurry image. In computer tomography, we have line measurements according to the Radon transform. So every line here you see is basically a projection onto a certain line in this CT image here, or in Fourier, in magnetic resonance imaging, we have actually measurements in the K-space, which is basically a Fourier domain, and we have a sparse sampling indicated by the red lines here in the Fourier domain. But all those operators are linear operators and they fall into our framework. So now let me turn to the modeling of the prior term, which is actually a little bit more complicated, especially for images. Let me briefly talk about the statistics of natural images. So for this, I start with something very simple. I consider a composition or a database made of 2 × 2 patches, so 4 pixels, which I have extracted from natural images. Here you just see a subset of those patches I've extracted from a natural image database, and this is how they look like. Actually, if you assume 256 different gray values, you can compute that there are a few billion possibilities for 2 × 2 patches. And you can easily see that this number will grow exponentially to larger and larger patches. So it will never be possible to render all different 8 × 8 patches, for example. So we would like to visualize the statistics of those patches because this bunch of images here is not very informative. For this, we follow the work of Lee, Peterson, and Mumford of 2003, where we actually project each patch onto a discrete cosine transform. So here you see the basis functions of a 2-dimensional 2 × 2 discrete cosine transform. And it turns out the first filter, which is just the DC component, can be safely ignored because we actually would like that our statistics is invariant with respect to radiometric translation. So we would like to consider just mean average patches. And you also see that the other filters simply correspond to edge detectors, horizontal, vertical, or diagonal edges. And they will carry on the statistics of the edges or the structures and images. So when I project all the patches onto these basis vectors and I make a 3-dimensional density function, or basically the negative log of the density function, and then I can visualize the 3D distribution. And this is what I did here. This is a certain ISO level of the 3-dimensional function. Here below, actually, I have plotted the densities of certain slices in the 3D space. The basic thing what we see is that the statistics is very non-Gaussian. So trying to model the statistics of image patches with Gaussians is a very bad idea. And this is actually well known. What happens if I take the statistics and I normalize it by its norm? So I get new new vectors y tilde, which have length 1. Then basically I have projected the density function to the surface of a 3-dimensional sphere. And when I unroll the 3D sphere, you see this very nice pattern occurring of the statistics of 2 × 2 patches. And actually we see there's a lot of structure in the statistics of images. And the basic idea of finding good models is that we try to find a parametric model that can reproduce those fine scale structures of the statistics. In 2 × 2 patches, one can see that this is somehow manageable, but if the patches become larger and larger, then this is actually a very difficult task. Something what we can also do is that we take the 3-dimensional density function and we compute its marginals. For example, with respect to the filters F2, F3, and F4. And if I plot the negative log marginals, I end up with these 1D functions here. The first filter, second filter, and the third filter. And what we observe is that the negative log marginal is heavy-tailed actually. And heavy-tailed means that most of the patches have no edges. And this corresponds to a very common assumption in images, that images are piecewise constant functions. So you have mostly constant regions with sharp edges in between. But when you look to more realistic images, natural images, you see that the statistics looks like those functions here. A widely used approach in order to parameterize such heavy-tailed log marginals is to make use of exponential distributions that factorize over its marginals. So we see, or we say that the distribution over the patches is given as the product of exponentials, and every exponential is minus some potential function, which is basically the energy of the projections of the patches onto those filters. And when I take the negative log of this term here, I end up that the regularization term of the patches is just the sum over potential functions of the patches projected onto the filters. So what are good functions to serve as models for those marginals? The most simple choice would be the quadratic function. And here on the right-hand side in black, you see the true marginal, and here you see the quadratic function, and we immediately see that this is completely off. And we have already seen before that the statistics of natural patches is completely non-Gaussian. If we take the absolute function, it's already closer, but it's still off. And it turns out that other functions, for example, the square root of the absolute of the filter response or the log student t function, are much better models. And this has, for example, been observed quite a long time ago by Huang and Mumford. Since we always hesitate between convex or not convex, that's the question. A good trade-off between model fit and complexity seems to choose the absolute function. Rho of t is absolute of t. Of course, I would also like to mention we don't need to factorize over the simple filter responses. We can also consider a function acting on all features at the same time, and therefore the equivalent simple choice for the absolute function would be the 2 norm. And later we will see that actually we can get much better results when we turn to non-convex learned potential functions. So far we have only restricted our statistical models to small patches of size 2 times 2. So how can we go to whole images? And since we want our patch statistics to be translation invariant, spatially in the image, so we don't care if an edge occurs in top left or bottom right corner or in the middle, we represent the filter correlations, the projections of the filter of the patches onto the filters by means of 2D convolutions. So we simply say that we convolve our image U with the filters Fk. And then the corresponding model is just the sum of all image pixels of the responses of the filters, then going into the potential function and summing up over all filters with corresponding potential functions. A very fundamental set of filters is obtained if F1 and F2 are simple discrete derivative filters. So they are finite differences, approximations of gradients. For example, with forward differences like this one, this corresponds to convolving our image with those filters where -1 is black and +1 is white. And if we adopt a convex potential function here, the 2 norm, this leads to the following fundamental image prior model where the potential function is nothing else than the magnitude of the image gradient. So it's the square root of the finite differences squared. And most of you have recognized which kind of model this corresponds to. Yes, this is nothing else than the total variation, which penalizes the total amount of edges and images. And by minimizing the total variation, we induce sparsity in the edges. And this is basically a piecewise constant image assumption. The regularization term will of course be very large if there's a lot of variation, such as noise in the image or texture, and the regularization term will be small if the image is flat, piecewise constant. One of the main properties of the total variation is that it can identify and preserve the most prominent edges in images. So when you start minimizing the total variation, you keep the most important edges in the image. And therefore it has had many applications in inverse problems like image denoising, image deblurring, optical flow estimation. Here is a color-coded flow, stereo imaging, or segmentation. So when we make use of the total variation prior for image denoising, a very famous model comes into play, which is the so-called ROF model, which is due to Houdin, Osh, and Fatemi of 1992. And it's defined as the following minimization problem. It's some regularization parameter lambda times the total variation plus a quadratic data fidelity term. So it means the likelihood assumption was Gaussian noise in our noise image D. And we make use of the prior given by the total variation. And the total variation denoising model is nice because it is quite simple, but still is very effective, so that it gives you a very good trade-off between simplicity and model quality. And it also served as the prototypical variation model in the mathematical image processing community. Over the years, it has been extended in numerous ways. I just mentioned here the TVL1 model, or the extension to oscillatorial patterns, or higher order smoothness assumption, and so on and so on. It was also quite stimulating for the optimization community, because the total variation term is non-continuous differentiable. So you need to think how you can actually find the minimizer of this problem here. And therefore people were thinking about how, or were developing algorithms that can efficiently minimize the ROF model. And I'm just mentioning here that there are duality-based approaches of Antonin Jambol, then the work of Pierre Weiss and co-workers, where they first applied Nesterov acceleration schemes, or the famous Fista algorithm due to back in the pool. And also primal dual algorithms, which are a little bit more general because they also work in the completely non-smooth case. So let us look at an example. I selected an image that later in learning has never been in the training database, so that we can really see if the trained models actually perform well also on images that are quite different. On the left-hand side, you see the original image. On the right-hand side, you see the noisy image. And when you do a ROF minimization, you end up with a result like this. The parameter lambda has been chosen such that it gave optimal denoising quality. We see actually it works quite well, but it also has some problems. For example, the well-known staircasing artifact, which tries to put the image as a piecewise constant function, or small scale structures are lost, and so on. This can be seen even more prominently when we switch to a different image restoration problem, which is image inpainting. Here I'm trying to recover the image from only 10% of the input pixels. White pixels in the background mean they are not known. And this is a result that total variation minimization gives us. So actually there's no data fidelity term here used. It's just the prior that comes into play here. And we see that it has many problems, for example, destroying the stick of Einstein's violin, or small scale structures, or in the hair or the eyes are completely lost. So therefore there's a need for a much richer model, because there's simple total variation models doesn't seem to capture the complexity of natural images. And one model that was quite influencing to me and my group is the so-called fields of experts model, which dates back to the work of Zhu and Mumford, and Roth and Black, and Samuel and Tappan. So basically we have already seen the structure. We have a potential function, we have filters, and now we are not restricting the filters to be edge detectors and the potential functions to be two norms. We would like to learn them from data. So filters can be, for example, DCT2 eigenvectors as visualized here, and the potential function could be log-student t-distribution, but later we would like to fine-tune them by learning it from data. So something that's interesting in the learning, we will parameterize the student log-student d functions with some parameters alpha and beta, and with those two parameters actually you can change the shape of the function between a convex and a non-convex function. So how should we perform learning? In 2014, with a PhD student, Yunjin Chen, we actually made use of bi-level optimization that has been used several times before in the literature to learn the potential functions and the filters of the aforementioned fields of experts model. For this, what we did is we considered training data consisting of ground truth images Gn and corresponding noisy images Dn. Dn was the data. And we set up the following bi-level optimization problem, where we said we would like to learn the best parameters theta corresponding to the filters and the potential functions, the shapes of the potential functions, such that the minimizers of the fields of experts regularizer plus a quadratic data fidelity term, because here actually we made the assumption that we have Gaussian noise, minimizes the higher level loss function J of theta. Okay, so you see it's a bi-level optimization problem because it's a nested optimization problem. We have an upper level problem, which is the reconstruction loss, and we have a lower level problem, which is actually computing the map solution of our statistical model. So how can you compute gradients of the higher level problem with respect to the parameters? For this, you have to basically make a sensitivity analysis, which is tantamount to implicit differentiation. And for this, you need to solve the lower problems with high accuracy. This I call a forward. And then after doing that, you have to solve for the adjoint state. And for this, you need to invert the Hessian of the lower level problem. And this corresponds to the backward. And in order to solve the lower problems with high accuracy, actually you need non-convex optimization algorithms which can deal with this optimization problem. For this, we, for example, developed together with Pedox, Thomas Box, Yunjin Chen, the IP2 algorithm. So here you have, you see some results of the learning procedure. So we used 48 filters of size 7 × 7 and the corresponding potential function. So altogether it was 2,400 parameters. And on the left-hand side, you see the filters. You see their oscillatorial patterns, their edge detectors, like in the total variation, as well as some directional derivatives. And on the right-hand side, actually, you see the corresponding potential functions. And what we can observe is that the potential functions corresponding to the texture filters are more convex, and the potential functions corresponding to the edge detectors are more non-convex. Let us compare it now with the simple total variation prior. Again, the noise image. This was the result of the ROF denoised image. And this is actually the result you can get with the learned model. And you clearly see that it significantly improves the quality. So there's a drop of the PSNI almost 2 dB here. We can also switch to the second task, which was inpainting, and here you see that the result is even better. So this was the result of TV, and this is the result of the field of experts prior. And here I would like to mention that the prior was just learned for image denoising, and we applied it for a different task, which was image inpainting. At this time, we also did our homeworks. We evaluated it with respect to the state of the art at that time, and it turned out that a model that had 9 × 9 filters was almost or as good as the state of the art at this time, although you have seen it's just a simple model consisting of filters and potential functions, and no further engineering was involved there. So one of the problems of the bi-level optimization is that it's heavily time consuming. So it took 2 weeks to learn the largest model at this time. And we also found out that the performance of the learning strongly depends on the error of the stationary point U star. So if we were not able to solve for the U star with very high accuracy, then actually we had noise in the gradients for learning, and the learning did not work very well. And usually 100 to 200 iterations are needed to solve the lower level problems. And this permits, for example, real-time applications. And idea to overcome this problem is so-called unrolling. The main idea is that you replace the stationary point U star that was used in the bi-level optimization by the result US, which is obtained after performing S steps of a minimization algorithm of your choice. For example, simple gradient descent. So this idea appeared in the literature first by Barbu for the fields of experts model, where they did a truncated minimization. In the field of sparsity in compressed sensing, it was due to Gregor and LeCun, and then you see that many different works followed this idea and came up with different approaches. So when we look at the bi-level optimization problem, we actually see that it's no longer a bi-level optimization problem, because we simply have a composition of functions that we just put to replace the stationary point U star. And we do this for a number of S iterations. So it has 2 main advantages. First of all, we can compute the exact gradient with respect to the model parameters. So this is just the chain rule or backpropagation. And when we specify the number S of iterations, the learning tries to make out the best of S steps. So we can say how many steps we have time to perform, and then it makes out the best of those steps. And there's another similarity to recent convolutional neural networks, and therefore we termed those truncated minimization as variational networks. So here you see that you start with the input to your variational network, then every step is nothing else than one gradient descent, which consists of convolving your image with your filters. Then you apply the nonlinear function, which is just a gradient or the derivative of your potential function, and then you convolve it again with the adjoint of your filters. And there's another branch where you have something that is nowadays called the data consistency layer, or it's simply the gradient of your data fidelity term. This gives you the next iteration, and you do this for S steps until you get the output of your network. It's interesting that there are very close connections of such variational networks to residual convolutional neural networks due to He and colleagues. One of the main things of the residual convolution networks is this additional branch here, which allows you to propagate information also from over the step, basically, and this allows to learn with many different steps. In a related work by Haber and Rototo, they have shown that this kind of networks are basically discrete versions of ordinary differential equations, and the theory confirms the stability of such architectures. So of course, a pressing question is how many steps, iterations, or layers should we take? And in order to answer this question, in more recent work together with Erich Kobler and Alexander Effland and Karl Kunisch, we consider the problem of selecting the number of layers as an early stopping issue with an optimal control problem in a continuous time setting. So for this, we replace the discrete iterations. So this f of us is just a placeholder for the gradient of the variational model, becomes an ordinary differential equation in a continuous time setting. So therefore, the learning problem looks as follows. We still have our higher level loss function here, and un of t is the result of the ordinary differential equation where t is between 0 and t. So how can we visualize this kind of problem? Assume we have some ground truth here, and this is the initial value of our ODE. Then the higher level problem, if you use a quadratic function as here in this example, you actually see the level sets of this function. In bilevel optimization, actually we try to find parameters that give us a trajectory such that u of infinity, so the stationary point, is as close as possible to the ground truth image. But here we additionally allow early stopping, so it means we are looking for the trajectory, but the u of infinity doesn't necessarily have to lie close to the ground truth, because we have an additional degree of freedom that we can select the early stopping of our image trajectory. In order to learn the optimal stopping time, we make use of a rescaling trick. So we reparameterize the image trajectory with this capital T, the stopping time. And therefore, here in the loss function, we are only interested in u of 1, because we, by the reparameterization, we say that at time 1, we have the final result. And it turns out the rescaling just rescales the speed of the gradient. So the t appears in front as a scaling parameter of the gradient of the variational model. And now the t is running between 0 and 1. And we showed that there's a first order necessary optimality condition for optimal stopping, which basically tells us that on average, with respect to time and number of training examples, the adjoint state of the ODE has to be orthogonal to the time derivative of the image trajectory. And this also visualized here in this image here, that you see that here is the ground truth image and the early stopping is here, and this is orthogonal to the trajectory, so the tangent of the trajectory, I have to say. And at the optimal stopping time, actually the 0 condition is fulfilled, and this corresponds to the minimum of the loss function J. We also confirmed this experimentally. So actually, in order to solve the problem, we need to discretize the ODE on the time interval 0, 1, and we need to discretize it into a number of S steps. And the number of S steps just has to be large enough such that we can ensure stability of our scheme. This is a simple Lipschitz condition on the gradient of the variational model. And as you can see, we allow more and more and more steps, but the performance in terms of PSNR has saturated after, let's say, 10 or 20 steps. And additionally, also the time the trajectory wants to go saturates regardless if we make more and more and more steps. So this confirms that actually the model likes early stopping. Here are the learned filters and functions of such a early stopping fields of experts model. On the left-hand side, you see the filters. And here, additionally, we made use of a higher parameterization of the potential function where we allow a more free shape of the potential functions. Altogether, the model has 3,841 parameters. What we see is we have truncated convex potentials as well as multi-well potentials. So here again, our Einstein test image, noise image. This is the result of the fields of experts, where we use Bilevel optimization, where we needed 200 iterations to find the solution. And now with the early stopping, we can get more or less the same result in just 10 steps. So you see the PSNR is a little bit higher, but of course we only needed a fraction of the time to compute the result. In very recent work, we proposed a new learned regularizer, which we term total deep variation. And I have to say that this new regularizer is not based on the factorization assumption over its marginals. The total deep variation regularizer is the sum of a pixel-wise deep variation. So we have in every pixel of the image, we have an energy term, R of u and theta. And this energy terms is computed by means of a deep neural network that consists of several residual blocks with coarse to fine scheme and with filters and potential functions. We also set it up as an optimal control problem in order to compute the optimal stopping time. And here we made use of a semi-implicit discretization of the gradient flow, which then ends up in a proximal gradient-like scheme. So here you have the gradient descent with respect to the regularizer, and here you have the backward step with respect to the data fidelity term. Of course, if A is just identity, then this step to invert is trivial. And in order to learn the parameters theta of the total deep variation, we set up a discretized mean field optimal control problem, which is the expectation over all ground truth images of our class of images we would like to reconstruct, and noise over the loss function. And what we have shown in the paper is that actually the minimum is attained of this problem, and for this we need to assume that the loss function is differentiable coercive, and we have some compactness assumption to the spaces of the learned parameters, and we also need to make sure that the TDV is twice continuously differentiable and has Lipschitz continuous gradients. For the optimal stopping time, we now have a formulation similar to the previous one, but this is now discrete. First of all, here is the expression how the adjoint state PS can be computed. And it's given with this backward scheme where we initialize with the gradient of the loss function, and then the previous steps are computed with this formula here. And it turns out that this is nothing else than the standard backpropagation algorithm just adapted to our particular setting here. And we again have a first order necessary optimality condition, which tells us that the adjoint state should be orthogonal on average with respect to the derivatives of the image trajectory, discretized derivatives in a certain metric induced by the data fidelity term. So let us now see how well the TDV works for image denoising. This is the result computed by the fields of experts model, the variational network, in 10 steps. And this is the result that is computed by the total deep variation, again in 10 steps. And we see that it gives almost perfect results, and I would say that the image looks even nicer than the original image. And also you see that the PSNR dropped than more than 1 dB. We also compared recently the results with respect to the state of the art, and it turns out that the TDV model is on par with the state of the art while having only 1% of the parameters to learn. We can also apply the learned regularizer, which we have learned for image denoising, to other inverse problems like computed tomography. So we just set up this variational model with a different data fidelity term and used the total deep variation regularizer here in front. And here you see the results from 8 times undersampled CT compared to the fully sampled reconstruction. And similarly, we can also do it for MRI. Just changing the linear operator, you see the result of the TDV regularizer from 4 times accelerated MRI. 4 times accelerated means every 4th line actually skipped in the K-space. So image super resolution, it turns out that works better if we learn the TDV regularizer together with the task. So it's a task-aware regularizer. And here you see the downscaled images, and this is a result of total deep variation regularization. When we compare this to the true images, of course, we see that there's a loss of details, but you know, this is impossible without hallucination to reconstruct those details which are missing in the downscaled images. So the last thing I would like to mention is how we can analyze the total deep variation. So we performed, for example, a nonlinear eigenmode analysis of TDV. If we just consider linear eigen values and eigenvectors, we see that this is equivalent to saying that the gradient of this quadratic energy is equal to lambda times u. Lambda is the eigenvalue, u is the eigenvector. And the generalization to nonlinear problems is given by exchanging the quadratic energy with an arbitrary energy, and here we take the energy of the total deep variation regularizer, which has been learned, for example, for Gaussian image denoising or super resolution. So how can we compute those eigenvectors u and eigenvalues? We set up a nonlinear least squares problem and try to find that u that minimizes this nonlinear least squares here. Lambda of u can be computed with this expression here, and this is nothing else than a generalized Rayleigh quotient. So why are eigenvectors, nonlinear eigenvectors, interesting? For example, let us be an eigenfunction which we have computed, and let's consider a gradient descent scheme with such an eigenimage. And it turns out that the eigenimages have the property that they only change the contrast of the image in the iteration. They don't change the structures. So they are structure keeping functions. How do such eigenimages look like for learned TDV models? Here you see some input images, which we use to initialize the nonlinear least squares. And this is the kind of eigenimages given for color Gaussian image denoising. And they somehow tell you the properties of the learned total deep variation. So the learned total deep variation likes piecewise constant images or smooth images, but it also likes straight edges. So it has also some curvature minimizing property, and it also likes texture. In contrast, when we visualize eigenimages corresponding to a total deep variation learned for super resolution, it turns out that their eigenfunctions actually hallucinate texture to the images. For example, look at the bear and the eigenimages, they start to introduce more texture. And this is natural because they should put more texture to the images. We also try to find out how robust the learned total deep variation regularizes against adversarial attacks. And therefore we set up an optimization problem where we try to find a bounded attack A such that the result after performing S steps of the total deep variation maximizes the distance, quadratic distance to the ground truth images. Here you see some ground truth images, the noisy input, and then we try to find attacks with bound epsilon1 or epsilon2 such that the square distance becomes as large as possible. And it turns out that, of course, you can compute such attacks, but they need to be quite structured. So they need to correspond to image structures looking like or similar to natural images. So we were not able to find just tiny noise attacks that completely destroy the output of the images. But this is due to the fact that per definition, every layer is one Lipschitz, because this is, otherwise it would not be a stable minimization procedure. For a larger bound, we see that the formation of these dot-like structures, and of course they destroy the output, but they could correspond to natural image structures. We also tried to find an empirical bound on the generalization error. So the generalization error is the difference between the expected error and our empirical error. So this is basically our training database, and this would be virtually all images. Of course, we don't know them. In order to get an empirical bound on the generalization error, we try to find worst case images, GQ. So those are images that are very hard to denoise. And we tried to find those worst case images that have a bounded total deep variation. So for example, we computed on our training database quantiles of energy values. And then we said, okay, what's the worst case GQ image to denoise that has a total deep variation less than VQ? And this clearly gives us a bound on the generalization error. So here you see worst case images to denoise for quantile 0.1. So 10% of all images of the training database had a total deep variation of the ground truth images less than this image. Here is 50%, and this here we have 100%. And when we start to denoise these images, and they have been computed to be resistant as possible to the total deep variation, we get denoising results like this. You see, okay, it's really hard to denoise, but they are not completely off. And on average, we see that the performance drops by 5 to 10 dB. So this already brings me to the conclusion. So I was talking about variational models appearing as map estimates from Bayesian approaches. They have a long tradition. They are quite well understood, but as I have argued, they're still too simple to capture the complexity of natural images. And also they have a high computational effort to solve the models exactly. Then in order to get rid of those problems, we came up over the years with so-called variational networks, and they are obtained from early stopping variational methods. And they work as good or even better than solving the variational models exactly. They have a very high flexibility and a low computational complexity. And deep variance, for example, the total deep variation, also yields state-of-the-art performance. For future work, we are currently considering generative versus discriminative learning. We're also trying to make use of unsupervised or at least semi-supervised learning. And for inference, we would like to replace the map estimation by means of Langevin-based Markov-Chain Monte Carlo methods or Bayesian variational networks. So with this, I would like to thank you for your attention. So I would like to mention that the content of this talk appeared from 10 or more years cooperation with great friends, colleagues, postdocs, PhD students, and without them it would not be possible to make this work. So thank you very much.
Yeah, okay. Many thanks for your talk. I switched the camera on, I think. Okay. So, yeah, I've just heard that the QA is open now. Okay, okay, good, great. Okay. Are there some questions? You can pose the questions directly. I think the best thing is to pose it via QA. You can also do it via chat, but QA may be better. And Tom said he wants to read the questions and immediately he wants to answer it. So there is one question, Tom, I think, and maybe you read it and do it yourself. Okay, yes. Daniel Kramers, yes.
Daniel is asking, when applying TDV to super resolution, you mentioned that it is best trained in a task-specific manner. Does that imply that you no longer have a clear separation of organization in data term? This is a very good question, Daniel. Thank you. Actually, what we're learning, task specifically, it's a discriminative prior. So you're completely right. So this is like, you know, generative versus discriminative models. For example, logistic regression is a discriminative model. When we learn it in a task specific manner, we know actually the kernel of our linear operator actually. So. And of course, if it's Gaussian denoising, the prior has to know different things than we do inpainting or MRI reconstruction. And exactly the thing actually we have seen for super resolution. We still have a clear separation between the regularizer and the data term, because we still use that it's a sum of both terms, and we still can say this part is coming from the data fidelity term and this part is coming from the regularizer. And therefore I mentioned in the future work we are currently investigating generative methods for learning in order to see the difference, but I'm pretty sure that generative learning will never be as good as discriminative learning, because this is known in machine learning for many, many years.
Okay, thank you. Are there more questions? Maybe Daniel, it's okay now with your question. If not, then Stacy should put you on mute, and then you can add something or what you want.
Thomas, I have a question, if I may. Mm-hmm. I wrote it on the chat.
Maybe you pose it directly.
Yes, I couldn't enter it into the Q&A. Anyway, you are fusing classic knowledge and image processing with deep learning, which is beautiful. This is the kind of work I prefer to see. But the honest question I have is, do we really need this fusion? I mean, the state-of-the-art results that we have today in image processing in those problems, for example, are all obtained using the brute force approach. The arbitrary network, massive databases, and long training. So can we ever compete with those methods? What is the future of this fusion that you're so much insisting on?
It's a good question. So I think that in the end, if we have enough data, we can never be better with those approaches. I think that's out of reach. But something I like in what we did is we at least have an energy, and the energy can be linked to a probability. And once you have a probability, then you are in the Bayesian setting, and then you can start to do different things. For example, why do we want to have a point estimate? So a reason that we are currently investigating Langevin diffusion type of schemes is because we want to show the medical doctors different realizations of the index problem. So I've prepared here a short video that has been produced by a PhD student, Dominik Nahnhofer. Now, I hope you can see it. So what you see here is...
Tom, can you put your camera a little bit in a different way, because we see just the upper part of you? Okay.
Okay. So on the left-hand side, actually, you see a video of MRI reconstruction, but different realizations. And this gives you some information where there are uncertainties in your data. And on the right-hand side, you see the variance, actually. And you see there's a lot of uncertainty in this area here. You see also it's flickering a lot. Or, for example, this structure here seems to be quite uncertain. I mean, the thing is also, if we want to have structure and we want to understand the structure, I think there's no way around that we try to match it with known theory that has been out for many, many years, and not only do the brute force way. And how we will ever have a chance to understand what's going on in the big black box. So you know all these adversarial attacks and so on. So just changing randomly some pixels, you can completely get crazy with your output. And here, by using the structure, every layer is one dipshit. So it means it's stable by itself.
Okay, thank you very much.
Okay, thank you.
Okay. There is are there some more questions? So I think we are approaching 1 hour now.
Tom, I don't know, can you hear me? I would have another question.
Who is it?
This is Daniel again.
Oh, Daniel, okay.
Now over speaker. I wanted to follow up Mickey's question. You know, obviously the naive or the popular approach to solve many of these problems today is just to train a network end-to-end to do that task. And I was wondering, what is the benefit of indeed creating this total deep variation and combining it with the data term? Typically, in the classical variational methods, you have, you know, results on existence, uniqueness, stability, etc. of minimizers. Can you deploy similar results with the total deep variation? And is that maybe a benefit of going this direction rather than just training a network to the task plan?
Mm-hmm. So at least this is something we are trying currently. So for example, we did a stability analysis showing what happens with the output if we change the noise at the input, showing that the worst case bound here showing is in the reach of the natural variations of the images. And we also try to find out what happens, for example, with the stability with respect to the learned parameters. So if we slightly perturb the parameters. And the main thing here we need to know is the Lipschitz constants of the network or of the regularizer. This is something that comes into play. But of course, having results like in linear models or in L1 type of models, currently I have no clear idea how we can get to those results. But of course, there's some hope, and it would be wonderful to get similar results there. Currently, we just have more or less empirical results showing that those networks with the structure we imposing on are more stable.
Thank you.
So I hope it's answered somehow. So if there are no more questions, I think we have 1 hour now. So I want to thank Thomas again for the great talk. And yeah, so I close this plenary talk now, and I hope everybody have learned something, and see you next time, maybe in the next plenary talk. Bye-bye.
Bye-bye. Thank you very much,
Tom.
Gabby.